Hello, buddy. Welcome. So, today we are gonna work on problem 3. As usual, I'd advise you to read the problem, try to solve it first on your own, and only when you're completely stuck should you come back and look at this solution or explanation. So, we are going to define something, a group. Uh, Actually, we don't know if it's a group yet. So, but let G be a group, right? Let G be a group. We're going to define something called Z of G. Z of G is called the center. Well, let me write it at the bottom. So we're going to define something called Z of G, which is really the set of all elements in G that commute with every other element in G. That is, it is the set of all H, right? H and G, such that GH equals to HG for all little g in big G. Right? So what this is saying is that, like, if you have an element in the set G that commutes with every other element in the group, that element is in this set Z of G. And Z of G is sometimes referred to as the center. Right? So I guess a good idea would be to play around with this, but a good example would be, let's say, I'm going to give you a really trivial example here, right? So consider what are we going to try here? Let's say the integers under addition, right? That's a group we've been working with a lot. You get elements and you add them to each other, right? Well, notice every element in Z, every integer commutes with every other integer, and so Z of the integers will just equal to the integers themselves, because every element in the integers commutes with every other element. Right? There are sets where there's nothing that commutes. There are groups where there's nothing that commutes with anything else, right? But so it's up to you to explore a few examples. But as the lectures continue, you'll see more and more examples. However, let's get back to our problem. Our problem here is to, let me erase this first. We do have a task to complete. Our job is to prove that Z of G, the center, is a subgroup of G. Right? So once again, take some time to think about this problem, and only when you're completely stuck should you come over to check the solution. Alright, let's begin. Proof. Well, to prove that something is a subgroup, there are many ways you can do it, but we could try the very direct path here, right? So what we're going to do is we're going to prove the following. Our strategy is we're going to prove that Z of G is closed, right? And the other thing, that means basically if you combine any two elements of Z of G, multiply them with each other, you're going to get an element of Z of G back. And the other thing we're going to do is prove that for any x element of Z of G, any element of Z of G has the property that its inverse is also in Z of G. If we can prove that these two things are true, we'll have successfully proven that Z of G is actually a subgroup of G. Right? So let's get to it here. So let's prove closure first, that it's closed. So let H and J, Hj, be elements of the group. Not elements of the group, but another mistake. We want to call them elements of Z of G. Right? Well, what do we know? If these are really elements of Z of G, then it means that for all little g in G, for every element of G, it's certainly true that Hg equals to Gh, right? That's the definition of being an element of Z of G. You must commute with every element of the group G. It's also true that that's one. It's also true that for all G in G, Jg equals to Gj, right? That's also another true statement. Alright? This is just to help burn in the idea of what Z of G really is. So our task is to prove that it's closed. Well, to prove that it's closed, all we have to do is to consider Hg. Say, we need to prove that Hg, the product of the elements of Z of G, is also in Z of G. That will prove closure. Well, notice, right? For any G in big G, for any element of G, Hg times G equals to H times Gj, right? Why are we able to do this? Well, because by property 2, Jg equals to Gj, right? So J and G can commute. Well, what else do we know? We have property 1. Property 1 says H and G commute. So this is the same as G times Hj, which is really saying we have G times Hj. So that's saying that any element of G commutes with Hj. Sorry, any element of G commutes with Hj, right? That's actually accurate, right? So don't confuse the G's and the J's. I'm getting confused myself, right? So, well, if this is true, then that must mean that Hj is actually an element of Z of G, right? So, if this is true, then we are saying that Z of G is actually closed. Right? We've proved that Z of G is closed. Our next task, to complete our proof that Z of G is a subgroup of G, right? That's what we're trying to do, prove that Z of G is a subgroup of G. Our next task is just so that any element of Z of G also has its inverse in Z of G, right? So let's pick element. Let's pick an element H. Let H be an element of Z of G, right? Well, we know that Hg equals to Gh, right? Just reminding you what elements of Z of G mean. That is, Hg must equal to Gh for all G in big G, right? This H must commute with all elements of G. Well, our task is to prove that H inverse is also an element of Z of G, right? What does it mean for H inverse to be an element of Z of G? It means that for every little g in big G, we want it to be true that H inverse times G equals to G times H inverse. That is, we want H inverse to actually commute with all the elements, right? Commute with every element of our set G, right? If we show that, then it will mean that H inverse is also in Z of G, otherwise known as the center. So let's work with this equation though. This equation is our friend, because let me write it here. If Hg equals to Gh, right, then I can multiply the left hand side by H inverse. And now I have that H inverse times Hg equals to H inverse times Gh, right? And then further work shows us we can now multiply the right. Actually, we can simplify. H inverse times H is just the identity, and so this equation becomes G equals to H inverse Gh. Well, I can multiply the right hand side by H inverse. It's an equation after all. Then suddenly we have G times H inverse equals to H inverse Gh times H inverse? Well, H times H inverse equals to the identity. So this equation reduces to GH inverse equals to H inverse G, which is exactly what we're trying to show here. We're saying that what we're trying to show here, right? We said that for H inverse to be an element of Z of G, it has to commute with every element of the group. So H inverse then commutes with G. This statement is saying that H inverse commutes with every element of the group, right? So thus H inverse is an element of Z of G, right? And so we've proved. Right. So we've now proved that the second part, any element has its inverse in Z of G. Well, if Z of G is closed and every element has an inverse, then it is indeed true that Z of G is a subgroup of G, which is exactly what we've been trying to prove, right? And that means we're done with the proof here. Well, so what ideas helped us to solve this problem? This is important because solving a problem is good, of course, but more importantly, if we're going to go through the effort to solve a problem, then it's worth our while to learn as much as we possibly can from it. It will simplify our problem solving later on. So we might ask the question, what key ideas helped us to solve this problem? The main idea was understanding what it means to be an element of Z of G, or to be in the center. Right? It's called Z of G is called the center, right? And that means that you commute with everything. And we applied that property to an element H in G to prove that Hg equals to GH. We applied it to J to prove that JG equals to GJ. Right? We applied it again on the last part, right here, to prove that Hg equals to GH, and then used it actually to prove that H inverse commutes with every element of G. Right? So a key idea here in proving this problem was knowing what it means to be an element of Z of G. Right? That is understanding the problem, right? And it's often said that you can't solve a problem if you don't understand it. And so here, understanding the problem turned out to be the major impediment to actually solving it. And the other thing, of course, that we learned is that if you have any group and you look at the set of elements that commute with every other element in the group, well, that set also forms a group, and it's a subgroup of G. Right? So if you have any group, for example, you're trying to solve a problem and you have a group, and you want to think of a subgroup of the group, well, you don't need to think very far. Just get Z of G, the center, the set of elements that commute with every other element, right? So thank you very much for watching this video. I hope to see you on the next video.